Of all the processes in an oil refinery, the most important is distillation. It is the first step in turning crude oil into usable products. The process depends on boiling. When water is heated, its temperature rises to 212 degrees Fahrenheit and stays there. This temperature is its boiling point, and once it has reached it, the water won't get any hotter. From this point on, the heat is used to change the water into steam, turn liquid into vapor. As soon as the steam cools below the boiling point, it turns back into water. The vapor condenses. But every liquid has its own particular boiling point, determined by the size and shape of its molecules. In general, the smaller the molecules, the lower the boiling point. The larger the molecules, the higher the boiling point. The clear liquid is made up of small molecules and boils at 173 degrees. The dark liquid is made up of larger, bulkier molecules and boils at 363 degrees. This difference in boiling point allows the two liquids to be separated again after they are mixed. Here's one way to do it. Heat the mixture inside the tube so that both liquids are vaporized. And feed the mixed vapors to a column where they are cooled. Near the bottom, the vapors are cooled to just below the boiling point of the dark liquid. So it condenses here and can be drawn off. But it's far too hot for the vapor of the clear liquid to condense. So it rises until it too is cooled sufficiently to condense. At the top of the column, clear liquid is collected, and at the bottom, dark liquid. The clear liquid will contain a small amount of the dark, and vice versa. But these amounts are slight because their boiling points are far apart. But crude oil is a mixture of a great many different kinds of molecules called hydrocarbons. There are many thousands of them, and their boiling points lie so close together they couldn't possibly all be separated individually. Fortunately, it isn't necessary. Instead of regarding crude oil as a mixture of individual hydrocarbons, they are lumped into groups, each covering a range of boiling points. In oil refining, these groups are called boiling fractions, or just fractions. The top fraction goes to make gasoline. The next one, turbine fuel. The next, diesel fuel and home heating oil. The rest either goes to make industrial fuel oil or is separated into more fractions. To help understand the idea of boiling fractions, consider crude oil as a pack of playing cards, all shuffled up. The gasoline fraction can be thought of as the fours. The turbine fuel fraction as the sixes. The diesel fuel and home heating oil fraction as the eights. And the fractions with the highest boiling ranges, the queens and kings. Sorting crude oil into fractions takes place in fractionating columns. Separating all of them requires two stages: crude distillation and vacuum distillation. First, crude distillation. Through these pipes, crude oil is pumped continuously from storage tanks to a furnace where it's heated. But it's only made hot enough to vaporize some of it. When it reaches the column, the crude oil is a mixture of vapors and liquids. Once inside, vapors and liquids part company. The liquids fall to the bottom. They are the queens and kings, and will be dealt with later. Meanwhile, the vapors, the fours, sixes, and eights, rise. As they pass through the tray, they are cooled. When their temperature falls below the boiling range of the heaviest fraction, This fraction condenses on the tray and is withdrawn. The remaining vapors bubble through this liquid and rise to the next tray where they are cooled further, below the boiling range of the next heaviest fraction. This condenses, and it too is drawn off. The vapor that's left is drawn off the top of the column and condensed. There are several ways of separating the fractions. One way is to use bubble trays. On each tray inside the column are mushroom-shaped fittings called bubble caps. The hot vapors rise up through the stem and then back down underneath the bubble cap into contact with the liquid on the tray. If liquid and vapor are of the same fraction, the liquid will be cool enough to condense the vapor. Thus, if the liquid consists of 8s, the vapor that condenses will also be 8s. But if the vapor is of a lighter or lower boiling fraction, it will find this liquid too hot to condense in. So it will bubble through and rise to the next tray still as vapor. If the liquid consists of 8s, these bubbles will be 6s and 4s. In practice, however, the vapors are so closely intermingled, they never separate completely the first time. Some vapor which belongs on this tray is carried through with the lighter vapors to the tray above. Here it condenses, but now it's on the wrong tray. To return it to where it belongs, a steady stream of liquid overflows to the tray below. Since this tray is hotter, the 6s that come down are re-vaporized and again rise to the next tray. But it is the right temperature for the 8. This time, it stays condensed. This thorough mixing and separating goes on all the time as the fractions are sorted out. Liquids falling and vapors rising, all the way to the top. At the top of the column, it's coolest, and only the lightest fraction is left, the 4s. This vapor is condensed, but it still contains stray 6s. So here too a steady stream is returned to the tray below. The 6s remain in the tray, and the lighter 4s are re-vaporized. Only 2 trays have been shown here, each tray separating 1 fraction. But in practice, several trays are needed to separate each fraction efficiently. An actual crude distillation column may contain more than 50 trays. The top fraction goes to make gasoline. The next one down, turbine fuel. The next, diesel fuel and home heating oil. The liquid settles to the bottom as residue, but it still contains other useful products. The fractions in the residue boil at very high temperatures, some more than 1,000 degrees. At these temperatures, the molecules will crack apart before the fractions boil. To prevent this, they must be made to boil at lower temperatures, by vacuum distillation. When a liquid is heated, the pressure of its vapor increases. This pressure pushes against the pressure of the atmosphere. When the vapor pressure is high enough to overcome the atmospheric pressure, the liquid boils. But the atmospheric pressure on the liquid can be reduced by pumping out some of the air and creating a partial vacuum in the flask. The vapor pressure now has less resistance to overcome, So the liquid boils at a lower temperature. Here the pressure has been reduced enough to make the water boil at room temperature. Similarly, if the pressure inside a distillation column is reduced, the heavy fractions can be boiled at lower temperatures, so they can be distilled without their molecules cracking apart. From the vapor entering the vacuum distillation unit come more products. The lightest fractions go to the cat cracker. From the next fraction come wax and lubricating oil. The heaviest fraction remains a liquid and is withdrawn for processing into industrial fuel oil and asphalt. Distillation is the key process in a refinery. But distillation alone isn't enough. For one thing, the gasoline that's distilled directly from crude oil, called straight-run gasoline, by itself is not high enough octane for the modern car. For another, when enough gasoline, turbine fuel, and diesel fuel are distilled, a lot of heavy fuel oil is produced as well. By using another process, cracking, heavy oil can be converted into high-octane gasoline. Heavy oil is made up of molecules that can be represented like this. When heated to very high temperatures, their movements become violent. Eventually, they shake apart or crack. In cracking into smaller molecules, most of them also change their shapes and take on new properties. Most important of these properties is a higher octane gasoline. This reshaping process depends on a substance called a catalyst. A catalyst is any substance that stimulates a chemical reaction without itself being affected by it. Hundreds of substances do this. Some complex, some simple, like these pieces of copper. This demonstration shows how they work. These two liquids normally react very slowly when mixed together. Now add the copper. The reaction is speeded up. When the reaction is complete, the catalyst is unchanged and can be used again. Many catalysts are used in a refinery. One of the most important uses is a catalytic cracking unit, a cat cracker. The catalyst used here consists of silica and alumina in the form of a fine powder. To do its job effectively, each grain must present the largest possible surface area to the heavy oil that's to be cracked. Seen through an electron microscope, each of these grains resembles a sponge. The grains are so sponge-like, this small handful has a surface area of 6,000 square feet, the area surrounding the man. The catalyst also has to circulate freely in the cat cracker, and to do this it must be made to behave like a liquid. At rest, the powder is a solid mass and will support a metal object. But if gas or vapor is blown through it, it's churned up or fluidized. The wrench sinks, as if it were in a liquid. To do its work in the cat cracker, the catalyst must be heated to more than 1,000 degrees. Then, at the base of the unit, hot catalyst and heavy oil meet, and cracking begins. The heavy oil is immediately vaporized, and the vapor in turn fluidizes the catalyst. This mixture rises to the reactor. Here, the heat and the catalyst complete the cracking reaction. Before long, however, carbon forms on the catalyst, clogging the openings. This reduces the working area and makes the catalyst less effective. So it has to be cleaned. It's fed to a regenerator where the carbon is burned off. The burning also heats the catalyst back to its working temperature, and it's ready for use again. This is the cycle of the cat cracker. A steady flow of catalyst meets a steady flow of heavy oil, and cracking goes on continuously, producing the new shapes that make up high-octane gasoline. Besides gasoline, cracking produces petroleum gases and diesel fuel. All these products are passed to a distillation column where they are separated. But cracking doesn't provide enough high-octane gasoline to meet the demand. So low-octane straight-run gasoline is converted into high-octane gasoline by catalytic reforming. Straight-run gasoline consists mainly of short, straight molecules. To upgrade it, the shapes of these molecules must be changed, that is, reformed. As before, heat and a catalyst are required. And again, high-octane gasoline is produced. A catalytic reformer uses platinum as the catalyst. A thin film of platinum is coated on pellets of aluminum oxide, and these are packed in the reactors. But reforming requires a lot of heat, and the process has to be done in 3 or more stages. The straight-run gasoline is heated to more than 900 degrees and fed into the first reactor as vapor. As it passes through the catalyst, reforming begins. But so much heat is absorbed by the reaction that it stops before reforming is complete. When it leaves the first reactor, the vapor is only partly reformed, so it must be reheated and fed to the second reactor. Again, the vapor cools below its proper reaction temperature, and the reaction stops. To reform the vapor completely, it must be reheated once more and fed to the third reactor. Here, any remaining straight-run gasoline molecules change into those of high-octane gasoline. During most of these reactions, a lot of hydrogen is released. Its presence not only inhibits the formation of carbon on the catalyst, it is also valuable for use elsewhere in the refinery. These, then, are the principal refining processes: crude distillation and vacuum distillation, which separate crude oil into various products; cracking, which converts heavy oil into high-octane gasoline, and reforming, which converts straight-run gasoline into high-octane gasoline. But this is only part of the story. Other processes turn out additional products, as well as providing many raw materials for the chemical industry. All in all, there are thousands of products based on petroleum, and more uses are being developed all the time.